DNA low copy number was pioneered at the Forensic Science Service and is its prized technology. Like standard DNA fingerprinting, it produces an electronic printout called an electropherogram, where each peak represents what's known as an allele, the type of DNA carried by an individual at specific points along their genetic code. This is human DNA being copied in a laboratory for standard DNA fingerprints. The two strands of the double helix structure are unzipped. Then they're copied, so scientists have enough material to create a profile. The low copy number technique starts with such tiny amounts of DNA that it has to be copied many, many more times to work.
Extracting profiles from small samples is extremely complicated and controversial. In America, the FBI refuses to work with such tiny amounts of DNA because they believe the results are unreliable. 3.5 years ago, Sean Hoey was put on trial for the murder of 29 people in one of Northern Ireland's worst ever terrorist attacks. The case tested the science to its breaking point. The prosecution was built upon the allegation that DNA found on bomb detonators was Hoey's. One expert witness claimed that the chances of the DNA being anyone else were 1 in a billion. But Hoey was acquitted.
The OMA verdict couldn't have been more damning for police and prosecutors. At the heart of their case was forensic evidence known as low copy number DNA. But the judge severely criticised the way it was handled by police and presented to the court.
One of the problems with low-level DNA evidence is that the chance of contamination is much greater than normal. In this case, the judge said there was a high risk that the samples had been contaminated because the police had been thoughtless and slapdash in the way they'd handled them. Forensic scientists do everything possible to prevent contamination, but they can't legislate for any mistakes made by the police.
Just how great are the risks of contamination when you're working with low-copy DNA?
The risks are enormous, and we might see contamination anyway because it's such small amounts of DNA we're dealing with. And so we have specialised areas which are protected. This is one such room. Only particular people are allowed into this room. We have to have their DNA profile so we can monitor it for contamination. But what we can't control is what happens to those samples before we get hold of them. You know, we have no idea. They arrive sealed, but how have they been handled? Who has handled them? Under what conditions have they been handled?
There has been a consistent cycle. As each new generation of DNA technology has been developed, it's been brought into court by enthusiastic proponents who are genuinely excited about its potential to help solve crime, and often with very good reason. But there's also been a tendency for the proponents of these techniques to sometimes oversell and overstate what it can do, and in a desire to promote the technique in general, a tendency to ignore problematic applications of those techniques.
Dan Crane is seen as the world's expert on the use of low copy number as evidence. He's a veteran of many trials, including that of O.J. Simpson. He was in Belfast last month to talk to lawyers about his fundamental concerns over the low copy number technique.
The biggest problem is probably also its greatest strength. It's ultra-sensitivity. That ultra-sensitivity comes with two categories of problems as I see it. One category is that with low copy number testing there is a much greater flexibility associated with the interpretation of the evidence relative to what would happen with conventional DNA testing.
In essence, when the amount of DNA you start with is very small and you amplify that up by creating copies over and over again, the result becomes statistically less reliable. Astonishing though it may seem, those alleles, the peaks on the DNA printout, can drop in or drop out almost at random. And that means whoever's handling the result has to interpret it in a way that's simply not necessary with standard DNA fingerprinting.
I thought it was quite curious and concerning that at the same time that the FSS was turning up the dial to increase the sensitivity of their technique, they were lowering the bar that allowed them to distinguish between signal and noise. I think it's intuitive. It's something that almost anybody would understand, that if you increase the volume of a radio station, for instance, the level of static goes up. It doesn't go down.
For Dan Crane, the key moment in the Hoey case came when he eventually got hold of the electropherogram traces from the FSS. To demonstrate the problem, he compares possible suspects, Tom, Dick and Harry, with the low copy number trace used by the prosecution. This evidence trace has two peaks, or alleles. At the bottom of the screen, how the FSS has evaluated those peaks. The F means they're not sure.
And the question really then becomes, can an individual like this be excluded as a possible contributor to that evidence sample?
He runs through Tom, Dick and Harry. In all cases, there's reason to include each suspect because some of their alleles, or peaks, match the evidence sample.
Dick is actually Sean Hoey in this particular scenario. That is Sean Hoey's DNA profile. And so sure, he can't be excluded as a possible contributor to this sample, but it needs to be borne in mind that neither can Tom or Harry or any of a large number of other people.
The low copy number approach came into sharp focus at the Sean Hoey trial. A sample on a piece of tape on a car bomb was compared with profiles held on the national DNA database. It came back with a match, but to a schoolboy living in Nottinghamshire.
You know, it could be attributed to one or both of the two sets of problems that are associated with low copy number testing. The flexibility of interpretation could have resulted in something that wasn't quite a perfect match now appearing to be a perfect match. And also the fact that maybe it actually was that 14-year-old boy's DNA that was seen, but it got there by something completely independent of his having anything to do with this particular explosive device. You know, he shook the hand of somebody who shook the hand of a person who handled the evidence sample, and lo and behold, we find his DNA there.
Because of these random effects, it's become standard practice to repeat a low copy number profile 2 and sometimes 3 times. If the same allele drops in or out twice or 3 times, then that effect begins to look less random. But in the OMA trial, Dan Crane highlighted how the Forensic Science Service had produced different profiles on successive runs on the same sample.
The very same article of evidence was generating, depending on the sequence in which the tests were run and which combinations were used, was generating a different DNA profile, right? And so I think that's really quite remarkable.